Look up at the night sky. Right now, at this very moment, there are galaxies out there engaged in the most violent cosmic ballet you can imagine. They're colliding, merging, tearing each other apart. And the James Webb Space Telescope just caught something happening between two of these galactic titans that has astronomers questioning everything they thought they knew about how the universe works. Picture this: two massive spiral galaxies, each containing hundreds of billions of stars, are locked in a gravitational death dance that began millions of years ago. They're moving toward each other at speeds that would make a fighter jet look like it's standing still. And in the space between them, in that void where you'd expect to find nothing but darkness and the occasional wandering gas cloud, James Webb detected something that shouldn't be there. Something that's rewriting our textbooks as we speak. The galaxies in question are located approximately 400 million light-years from Earth. That means the light we're seeing from them left those galaxies when dinosaurs still roamed our planet. Think about that. The photons captured by James Webb's mirrors traveled through the vacuum of space for 400 million years, survived the expansion of the universe itself, and arrived at our telescope to tell us a story that began in an era so ancient that Earth didn't even have flowers yet. But here's where it gets interesting. When two galaxies collide, they don't actually crash into each other like cars in a demolition derby. The stars are so far apart that they mostly pass through each other like ghosts. Imagine two swarms of fireflies flying through each other on a summer night. That's what's happening on a galactic scale. But the gas and dust? That's a different story. That material slams together with tremendous force, creating shock waves that ripple through space like tsunamis through an ocean. James Webb was studying this collision with its infrared eyes, seeing through the dust and chaos to observe the birth of new stars. Because that's what happens when galaxies collide. The compression of gas clouds triggers one of the most spectacular fireworks displays in the universe. A burst of star formation. Thousands, sometimes millions of new stars igniting across both galaxies like cosmic sparklers. Astronomers call it a starburst. And it's beautiful. Violent, yes, but beautiful. But that's not what caught everyone's attention. Between these two colliding galaxies, in the space that should be relatively empty, James Webb detected a massive structure. Not a third galaxy, not a wandering black hole, something else entirely. A bridge. A cosmic bridge made of hydrogen gas, stretching across hundreds of thousands of light-years, connecting the two galaxies like an umbilical cord between twins in the womb. Now, tidal bridges between colliding galaxies aren't exactly new. We've seen them before. When two galaxies get close enough, their gravitational fields start pulling on each other's material, stretching out long streams of stars and gas. It's like cosmic taffy being pulled apart. These structures are called tidal tails or tidal bridges, and they're actually quite common in galactic mergers. The famous antennae galaxies have spectacular tidal tails that stretch for hundreds of thousands of light-years. But this bridge is different. This bridge is alive. The hydrogen gas in the structure isn't just sitting there, inert and cold. It's hot. It's glowing. It's forming stars. Lots of stars. The entire bridge is lit up with stellar nurseries, regions where new stars are being born at a rate that has astronomers scratching their heads. We're talking about an environment that by all rights should be too chaotic, too disrupted, too thin to allow star formation. And yet, there they are. Thousands of newborn stars blazing into existence in the void between worlds. Let me put this in perspective. When you look at typical star-forming regions in a galaxy, you need very specific conditions. You need dense clouds of molecular hydrogen. You need the cloud to be cold enough that gravity can overcome the internal pressure and collapse the gas into stars. You need protection from the harsh radiation of nearby stars that would otherwise blow the cloud apart. It's a delicate balance, a cosmic recipe that requires just the right ingredients in just the right proportions. The bridge between these two galaxies has none of those advantages. The gas is being stretched and pulled by gravitational forces that would tear apart any normal stellar nursery. The radiation environment is harsh, with massive stars from both galaxies flooding the region with ultraviolet light. The density of the gas should be far too low to allow gravitational collapse. And yet, star formation is happening. Not just happening, thriving. This is where James Webb's capabilities become crucial. Previous telescopes like Hubble could see these structures, but they couldn't peer through the dust to see what was really going on. Infrared light, the kind James Webb specializes in, passes right through dust clouds like X-rays through flesh. It allows us to see the hidden processes, the secret machinery of the universe at work. And what James Webb saw is extraordinary. The spectra, the fingerprints of light coming from this bridge, reveal something unexpected. The gas isn't just hot from the compression of the collision. It's being heated by something else. Young, massive stars, O-type stars and B-type stars, the heavyweight champions of the stellar world, burning so hot and bright that they live fast and die young, existing for only a few million years before exploding as supernovae. These stars are so powerful that they're ionizing the hydrogen around them, stripping electrons from atoms and causing the gas to glow like a neon sign. The entire bridge is lighting up with this process, creating what astronomers call an HII region. Pronounced H2. It's one of the most spectacular sights in astronomy. The Orion Nebula is an HII region. The Eagle Nebula, where those famous pillars of creation reside, is an HII region. They're stellar maternity wards, and they're some of the most photogenic objects in space. But finding an HII region in a tidal bridge between colliding galaxies? That's new. That's strange. That's exactly the kind of discovery that makes astronomers sit up in their chairs and say, wait, how is this possible? The mass of this bridge is staggering. We're talking about billions of times the mass of our Sun, all stretched out across the gulf between two galaxies. To put that in perspective, that's more mass than in some entire dwarf galaxies. It's enough material to build millions of solar systems. And it's all out there, suspended in space, forming stars where stars shouldn't be able to form. Now, here's where the mystery deepens. When astronomers started analyzing the chemical composition of the gas in this bridge, they found something peculiar. The metallicity, that's astronomer speak for the abundance of elements heavier than hydrogen and helium, was all wrong. It was enriched, enhanced, higher than it should be for gas that had been pulled out of the galaxies. You see, in astronomy, we have this concept called cosmic evolution. When the universe began with the Big Bang, it was almost entirely hydrogen and helium. Those were the only elements that formed in the primordial fireball. Every other element on the periodic table, from carbon to oxygen to iron to gold, was forged in the hearts of stars. First-generation stars formed from that primordial gas, lived their lives, and when they died, they ejected those newly created elements into space. Second-generation stars formed from that enriched material, created even more heavy elements, and the cycle continued. The gas in galactic disks, where most stars form, has been through many generations of this cycle. It's well-mixed, well-processed, enriched with metals. But gas in tidal bridges is supposed to be relatively pristine. It's been pulled out from the outer regions of galaxies, where star formation has been minimal, where the gas hasn't been processed as much. It should have lower metallicity. This bridge doesn't follow the rules. The metallicity is high, higher than the outer regions of either galaxy, which means this gas has been processed, enriched, run through the stellar furnace multiple times. But how did it get there? How did enriched gas from the inner regions of these galaxies end up in a bridge between them? There are theories, of course. There are always theories. One possibility is that the collision itself is more complex than we thought. Maybe there wasn't just one encounter between these galaxies. Maybe they've been doing this dance for a long time, passing by each other multiple times over hundreds of millions of years, each passage pulling more and more material out, mixing gas from different regions, creating this enriched bridge through a series of cosmic interactions. Another possibility is even more intriguing. What if the star formation we're seeing isn't the first generation? What if stars have been forming in this bridge for millions of years, going through their entire life cycles, enriching the gas, and then triggering new generations of star formation. It would mean this bridge is older, more stable, more long-lived than we thought. It would mean that these in-between spaces, these transitional regions between colliding galaxies, might be important sites of star formation and chemical enrichment in the universe. But here's the really mind-bending part: the velocities. James Webb, with its spectroscopic capabilities, can measure how fast gas is moving by looking at the Doppler shift of its light. Same principle that makes an ambulance siren change pitch as it drives past you. Light from objects moving toward us is shifted toward the blue end of the spectrum. Light from objects moving away is shifted toward the red. The gas in this bridge is moving in ways that don't make simple sense. There are multiple velocity components. Gas moving in different directions at different speeds. Turbulence, chaos, but also structure, organized flows. It's like looking at a river system from above and seeing multiple streams, eddies, whirlpools, all flowing in a pattern that seems random but has an underlying order. Some of the gas is moving toward one galaxy, some toward the other. Some is moving perpendicular to the bridge entirely, as if being ejected outward into intergalactic space. There's gas moving at hundreds of kilometers per second, and there's gas that seems almost stationary, caught in gravitational balance between the two titans. This complexity suggests that the gravitational dynamics of this system are far more intricate than simple models predict. It's not just two galaxies pulling on each other. It's a three-body problem, or actually a several billion-body problem, because every star, every gas cloud, every dark matter particle in these systems is contributing to the overall gravitational field. And three-body problems, as any physicist will tell you, are notoriously difficult to solve. Add billions of bodies, and you need supercomputers running for weeks to even approximate what's happening. But here's what really gets me excited. This discovery isn't just about one weird bridge between two colliding galaxies. It's about what this tells us about galaxy evolution on a cosmic scale. Because galaxy mergers aren't rare. They're not unusual cosmic accidents. They're fundamental to how galaxies grow and evolve. Our own Milky Way galaxy has been built up over billions of years by merging with smaller galaxies. We have evidence of those ancient collisions written in the movements of stars in our galactic halo. And in about 4 billion years, we're going to collide with our nearest large neighbor, the Andromeda Galaxy. That collision has already begun, in a sense. Our two galaxies are rushing toward each other at over 200 kilometers per second. The gravitational effects are already at work, even though we're still 2.5 million light-years apart. When that merger happens, and it will happen, our solar system will be carried along for the ride. The stars won't crash into each other. The odds of any star hitting any other star are astronomically small. But the gas will slam together. New stars will form. The supermassive black holes at the centers of both galaxies will eventually merge, releasing gravitational waves that will ripple through space-time itself. And structures like this bridge, these star-forming regions in the space between the merging galaxies, will light up our sky. Imagine being alive to see that. Imagine looking up at the night sky and seeing not just stars, but entire stellar nurseries spanning from horizon to horizon. New suns being born in real time, visible to the naked eye. The sky filled with nebulae glowing in every color imaginable. It would be the greatest light show in Earth's history. Terrifying, yes, because it would signal the end of our galaxy as we know it, but also beautiful beyond words. The discovery by James Webb is giving us a preview of that future. It's showing us what happens in the chaos of collision. And the message is clear. Where there's chaos, there's also creation. Where there's destruction, there's also birth. The universe doesn't waste anything. Every atom that gets pulled out of a galaxy finds a new home. Every gas cloud that gets compressed forms new stars. Every collision creates new opportunities for structure and complexity. Now, let's talk about the technology that made this discovery possible, because the James Webb Space Telescope itself is a marvel that deserves attention. This isn't just a bigger version of Hubble. It's a fundamentally different kind of observatory, designed from the ground up to see the universe in infrared light. The mirror is massive, 6.5 meters across, made of 18 hexagonal segments, each coated with a microscopic layer of gold because gold is the best reflector of infrared light. When you see those iconic images of James Webb's mirror, that golden honeycomb structure, you're looking at one of the most precisely engineered objects humans have ever built. Each mirror segment can be adjusted independently, moved by tiny motors with nanometer precision, to keep the whole system in perfect focus despite the extreme temperature variations of space. And speaking of temperature, James Webb operates cold. Really cold. The instruments are cooled to about 40 Kelvin, which is negative 233 degrees Celsius. Negative 387 degrees Fahrenheit. That's colder than liquid nitrogen. Colder than the surface of Pluto. Why so cold? Because infrared light is heat radiation, and if the telescope itself was warm, it would glow in infrared and blind its own instruments. It would be like trying to study fireflies with a searchlight. To achieve this temperature, James Webb has a sunshield the size of a tennis court. 5 layers of material, each thinner than a human hair, coated with reflective metal. This shield blocks the heat and light from the sun, Earth, and Moon, keeping the telescope's instruments in permanent shadow. The difference in temperature between the sun-facing side of the shield and the cold side is about 600 degrees Fahrenheit. That's the difference between the interior of an oven and the freezing point of liquid oxygen. The telescope sits at a special point in space called L2, the second Lagrange point, about 1,000,000 miles from Earth. At this location, the gravitational pull of the Earth and Sun balance out in just such a way that the telescope can maintain a stable orbit without using much fuel. It's like balancing a marble on top of a saddle. Unstable in one direction, stable in another. Small thruster firings keep it in position, but overall it's a very efficient place to park a space telescope. From this vantage point, James Webb can observe the universe 24/7 without the Earth or Moon blocking its view. It can stare at a single target for hours, days, even weeks if needed, collecting every precious photon that crosses the cosmos to reach its mirrors. And that's exactly what it did with these colliding galaxies. The observation took multiple sessions. First, broad-field imaging to see the overall structure. Then targeted spectroscopy on interesting regions, splitting the light into its component wavelengths to reveal the chemical composition, temperature, and velocity of the gas. Then more imaging in different filters to isolate specific emission lines, the signature wavelengths of light emitted by hydrogen, oxygen, sulfur, and other elements in the bridge. The data that came back was rich beyond imagination. Terabytes of information, every pixel in the images telling a story, every feature in the spectra revealing a secret. Astronomers are still analyzing it, still finding new details, still being surprised by what's hidden in the data. And here's something that really drives home how revolutionary this telescope is. James Webb can see things that are not only far away in space, but far back in time. The farther you look in distance, the farther you look back in time because light takes time to travel. The colliding galaxies in this study are 400 million light-years away, so we're seeing them as they were 400 million years ago. But James Webb can see much farther. It can see galaxies that are more than 13 billion light-years away, formed less than 1 billion years after the Big Bang. Think about that. We're seeing the baby pictures of the universe. Galaxies in their infancy, the first generations of stars lighting up the cosmic dark ages. Black holes forming when the universe was just a fraction of its current age. It's like finding a time machine that lets us watch the history of the cosmos unfold. And what we're learning is that the early universe was far more dynamic, far more complex than we expected. Those first galaxies weren't small and simple. Many of them were already massive and structured. Star formation was happening at incredible rates. Black holes were growing faster than our models predicted. The universe hit the ground running, so to speak, evolving and changing at a pace that challenges our understanding. The bridge between these colliding galaxies is a window into these processes. It's showing us that star formation can happen in environments we didn't think were suitable, that chemical enrichment can occur faster and in more varied locations than we assumed, that the space between galaxies isn't empty and boring, but dynamic and creative. Now, let's zoom out even further and think about what this means for the universe as a whole. We live in what astronomers call the local universe, the nearby cosmic neighborhood. When we look at galaxies in the local universe, we see mostly mature, evolved systems. Spiral galaxies with well-defined arms. Elliptical galaxies with old, red stars. The wild days of youth are over for most of these systems. But when we look back in time, to distant galaxies billions of light years away, we see a different story. We see chaos. We see mergers happening everywhere. We see irregular galaxies that don't fit into neat categories. We see the universe in its adolescence, going through growing pains, still figuring out what it wants to be. The bridge discovered by James Webb gives us a close-up view of those processes. It's too close to be truly ancient, but it's far enough away that we're seeing it as it was hundreds of millions of years ago, during an era when galaxy mergers were more common than they are today. It's a living laboratory, a natural experiment in galactic evolution happening right before our eyes. And here's the philosophical part that really gets me. We are made of star stuff. That's not just a poetic phrase. It's literal truth. Every atom in your body except hydrogen was forged in a star. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it came from stars that lived and died before the sun was born. Those stars expelled their enriched material into space. That material became part of the cloud from which our solar system formed, and eventually some of those atoms ended up in you. The processes we're seeing in this bridge between colliding galaxies, the star formation, the chemical enrichment, the creation of heavy elements, these are the same processes that made you possible. Billions of years ago, in some ancient merger between galaxies whose names we'll never know, stars formed in a bridge much like this one. Those stars lived and died. Some exploded as supernovae, scattering their atoms into space. Those atoms drifted for millions of years, eventually becoming part of a galaxy that would one day merge with another to form the Milky Way. And here we are, billions of years later, using those atoms to study similar processes happening in other colliding galaxies. It's a circle, a cosmic cycle of creation and destruction, life and death, synthesis and dispersal. And we're not separate from it. We're part of it, active participants in the universe's grand experiment. The data from James Webb also reveals something about the future of this system. The two galaxies aren't going to pass by each other and go their separate ways. They're locked in a gravitational embrace that can only end one way: merger. Over the next few 100 million years, they'll continue their dance, passing by each other multiple times, pulling out more tidal bridges, triggering more star formation, until eventually they merge completely into a single, larger galaxy. That final galaxy will probably be an elliptical, a smooth, featureless blob of old red stars. Most of the gas will have been used up in the starburst triggered by the merger. The spiral arms will be destroyed, scrambled by the gravitational chaos. The two central supermassive black holes will sink toward the center and eventually merge, releasing a burst of gravitational radiation. From the outside, it will look like peace, like calm after the storm. But that calm comes at the cost of the beautiful spiral structures we see today. It's the price of evolution. Growth requires destruction. Change requires sacrifice. Unless, that is, there's new gas falling in from outside. Because galaxies don't exist in isolation. They're embedded in vast halos of dark matter. And those dark matter halos contain reservoirs of gas that can fuel future star formation. The merged galaxy might not stay red and dead. Give it a few billion years, let some fresh gas fall in from the halo, and it might restart star formation. It might build new structures. It might evolve into something we haven't imagined yet. The universe is full of surprises. Every time we think we understand how something works, we find an exception. a strange case, an anomaly that forces us to rethink our models. This bridge between colliding galaxies is one of those anomalies. It's teaching us that the rules aren't as rigid as we thought, that creativity emerges from chaos, that the universe has more tricks up its sleeve than we gave it credit for. Now, I want to talk about what this means for other star-forming environments we might have overlooked. For decades, astronomers have focused on the obvious places: galactic disks where spiral arms concentrate gas, the centers of galaxies where density is highest, giant molecular clouds like the Orion Nebula. These are the stellar nurseries we know and love, the places we thought were the primary sites of star formation in the universe. But what if we've been missing a significant fraction of star formation because it's happening in places we didn't think to look? What if tidal bridges, galactic halos, the outskirts of galaxies, and even the intergalactic medium are contributing more to the cosmic star formation budget than we realized? James Webb's discovery suggests we need to expand our search. We need to look beyond the obvious. We need to map star formation in all its hiding places, not just the bright beacons we've been studying for years. Because if stars can form in a tidal bridge between colliding galaxies, where else might they be forming? There's already evidence of star formation in some truly bizarre locations. Stars forming in the outflows from active galactic nuclei, blown out by supermassive black holes. Stars forming in the debris of galaxy collisions billions of years ago, lingering in intergalactic space. Even stars forming in the local group, the small cluster of galaxies that includes the Milky Way and Andromeda, in the space between member galaxies. Each of these discoveries challenges the notion that star formation is a straightforward process that only happens under specific, well-defined conditions. It's messier than that. More creative, more opportunistic. Give the universe some hydrogen gas and a bit of gravitational compression, and it will find a way to make stars. This has implications for how we think about the distribution of life in the universe. Because where there are stars, there can be planets. And where there are planets, there might be life. If a significant fraction of stars are forming in non-traditional environments like tidal bridges, then a significant fraction of planets might also be forming in these environments. What would it be like to live on a planet in a tidal bridge between two colliding galaxies? Your night sky would be split between two massive galaxies, one on each side, each spanning enormous portions of the sky. Depending on your location, you might see spiral arms stretched and distorted, tidal tails reaching out into space, and new stars blazing into existence all around you. The sky would be bright, filled with nebulae and star clusters, a cosmic light show that never ends. But it would also be dangerous. The radiation environment would be harsh, with massive stars exploding as supernovae more frequently than in a normal galactic disk. The gravitational perturbations might destabilize planetary orbits. The whole system would be in flux, changing noticeably over timescales of millions of years. Would intelligent life emerge in such an environment? Would it have time to evolve before conditions changed too dramatically? Or would the constant stimulation, the ever-changing sky, the awareness of being in a cosmic transition zone, somehow accelerate the development of consciousness and technology? We don't know. We can't know. But it's fun to speculate. What we do know is that the universe is more diverse than we imagined. Life, if it exists elsewhere, might not just be on planets orbiting sun-like stars in quiet galactic suburbs. It might be everywhere, in every environment where chemistry can work its magic. And that makes the universe a far more interesting place. Let's return to the science, though, because there are specific details about this bridge that warrant deeper examination. The star formation rate, for instance. Astronomers measure this in terms of solar masses per year. How many sun-sized stars, or equivalent mass in larger or smaller stars, are being born annually in a given region? In a typical spiral galaxy like the Milky Way, the star formation rate is about 1 to 2 solar masses per year. That's right. Our entire galaxy, with its hundreds of billions of stars, is currently making only about 1 or 2 new stars per year on average. Most of the stars that exist now were formed billions of years ago during an earlier, more active phase. In a starburst galaxy, one undergoing a major merger or some other triggering event, the star formation rate can be 10 to 100 times higher. We're talking about 10 to 200 solar masses per year. These galaxies are using up their gas reservoirs at a prodigious rate, creating massive stars that will quickly enrich the interstellar medium with heavy elements before exploding as supernovae. The bridge between these two colliding galaxies has a star formation rate of approximately 5 to 10 solar masses per year, just in the bridge, not counting the star formation happening in the galaxies themselves, which are also undergoing starbursts. This bridge, this structure that shouldn't be able to form stars efficiently, is producing stars at a rate comparable to an entire spiral galaxy. And it's not just the rate, it's the distribution. The star formation isn't uniform across the bridge. It's clumped, concentrated in nodes and knots that are spaced somewhat regularly along the length of the bridge. Each knot is a few thousand light-years across, contains millions of solar masses of gas, and is glowing with the light of young, hot stars. These knots might be the result of gravitational instabilities in the bridge. When you have a long stream of gas being stretched between two massive objects, it can become unstable, fragmenting into pieces. It's like a water stream breaking into droplets. The gravitational field of the galaxies pulls on the gas unevenly, and certain regions become denser than others. These dense regions then collapse under their own gravity, forming stars. Or the knots might be seeded by something else. Dark matter substructure, perhaps. Wandering black holes. Pre-existing stellar clusters that were pulled out of one of the galaxies and are now providing the gravitational seeds around which new material accumulates. The data isn't yet clear on the cause, but the effect is undeniable. The bridge is lumpy, and those lumps are stellar factories. Another fascinating aspect is the age spread of the stars in the bridge. James Webb's near-infrared spectroscopy can estimate the ages of stellar populations by looking at their colors and spectra. Young stars are hot and blue. Middle-aged stars like the Sun are yellow. Old stars are cool and red. By analyzing the light from different parts of the bridge, astronomers can reconstruct the star formation history. What they found is that star formation in the bridge didn't all happen at once. It's been going on for tens of millions of years. There are regions with very young stars, less than 1 million years old, still embedded in their birth clouds. And there are regions with stars that are 10, 20, even 50 million years old, spread out from their original formation sites. This means the bridge has existed in some form for a long time. The collision isn't a single event, but an ongoing process. The two galaxies have been interacting for at least 100 million years, and the bridge has been forming stars for most of that time. It's a stable, or at least quasi-stable, structure that has persisted through multiple orbits of the galactic dance. That stability is itself surprising. Tidal bridges are generally thought to be ephemeral features, lasting only a few tens of millions of years before dispersing. But this one has hung around, continually fed by gas being pulled from the galaxies, continually forming stars, continually enriching its own material with the products of stellar evolution. It's almost like the bridge has become a pseudo-galaxy in its own right. It has mass, it has star formation, it has structure, it has chemical evolution, all the characteristics we associate with galaxies, except a central bulge and a supermassive black hole. Could structures like this be the seeds of new galaxies? Could they survive long enough after the merger completes to become independent systems? Probably not in this case. The gravitational pull of the merging galaxies is too strong. The bridge will eventually be incorporated into the merged galaxy, its stars becoming part of the stellar halo or disk of the new system. But in other environments, in collisions between smaller galaxies, or in more gently interacting systems, maybe such structures could escape and become free-floating. We might have dwarf galaxies in the local group that were born this way, pulled out of their parent galaxies billions of years ago, and then cut loose to evolve independently. It's another example of how diverse the paths to galaxy formation might be. We usually think of galaxies forming from the collapse of primordial gas clouds in the early universe, growing over time through accretion and mergers. But maybe some galaxies are born differently. Maybe some are the orphan children of violent collisions, cast out to make their own way in the cosmos. The chemical abundances in the bridge provide another clue to its history. As I mentioned earlier, the metallicity is higher than expected. But it's not just the overall metallicity. It's the pattern of abundances, the ratios of different elements to each other. When stars die, they don't release all elements equally. Low-mass stars like the Sun, primarily produce carbon, nitrogen, and some oxygen. They blow off their outer layers gently as planetary nebulae, enriching the surrounding space with these elements. High-mass stars, on the other hand, explode as supernovae, creating and releasing a broader range of elements, including oxygen, neon, magnesium, silicon, sulfur, and iron. The ratios of these elements in the interstellar medium tell us about the history of star formation. If you have a lot of carbon and nitrogen relative to oxygen, it suggests many generations of low-mass stars have lived and died. If you have a lot of oxygen and iron, it suggests more recent contributions from high-mass stars and supernovae. The bridge has a pattern that's consistent with recent, ongoing enrichment from high-mass stars. The oxygen abundance is particularly high, so is neon. These are classic signatures of massive stars and supernovae. It suggests that the star formation we're seeing isn't the first generation. There have been previous generations of massive stars in this bridge, and they've already exploded, seeding the gas with their ashes, setting the stage for new stars to form. It's a cycle. Stars form from enriched gas. They live and die. They enrich the gas further. New stars form. The cycle repeats, each generation building on the work of the previous one, each generation making the universe a little more complex, a little more interesting. This is universal process. It's happening here on Earth in a sense. The atoms we're made of have been through this cycle many times. They've been part of stars, part of interstellar clouds, part of planets, part of living organisms over and over for billions of years. We're temporary arrangements of matter that will eventually be dispersed and rearranged into new forms. It's sobering and beautiful at the same time. James Webb's observations also picked up something unexpected in the X-ray regime. Well, not X-ray directly because James Webb doesn't observe X-rays. But by combining James Webb's infrared data with X-ray observations from Chandra and XMM Newton, astronomers found a population of bright X-ray sources in the bridge. These sources are likely X-ray binaries, systems where a normal star is orbiting a compact object, either a neutron star or a black hole, and matter from the normal star is being pulled onto the compact object. As matter falls onto a neutron star or black hole, it heats up to millions of degrees and emits X-rays. These systems are beacons of high-energy physics, laboratories where matter is pushed to extremes that we can't replicate on Earth. And finding them in the bridge is another indication that the stellar population there is diverse and evolved. X-ray binaries form when a massive star goes supernova and leaves behind a neutron star or black hole, and that compact object then starts accreting from a companion star. The fact that we're seeing X-ray binaries in the bridge means that massive stars have already lived out their short lives and exploded, and we're now seeing the remnants of those explosions feasting on their neighbors. It's a reminder that star formation is just the beginning of the story. Once stars form, they evolve, they interact, they die, and their deaths shape the environment for the next generation. The universe is a network of interconnected processes, each feeding into the next, creating a tapestry of cause and effect that spans billions of years and billions of light years. Now, let's talk about the supermassive black holes at the centers of these two galaxies, because they're a crucial part of the merger story. Each galaxy almost certainly has a supermassive black hole at its core, millions to billions of times the mass of the Sun. As the galaxies merge, these black holes will eventually sink toward the center of the combined system and merge themselves. When supermassive black holes merge, they release gravitational waves, ripples in the fabric of spacetime that travel at the speed of light. These waves are incredibly powerful. A merging pair of supermassive black holes can release more energy in gravitational waves in a few seconds than all the stars in the observable universe release in light over the same period. We can't yet detect gravitational waves from supermassive black hole mergers directly. Our current detectors, LIGO and Virgo, are sensitive to higher frequency gravitational waves from smaller black holes and neutron stars. But future detectors, particularly the space-based LISA mission planned for the 2030s, will be able to hear these cosmic collisions. And when they do, we'll be able to study black hole mergers in a completely new way. We'll be able to measure the masses, the spins, the distances of merging black holes across the universe. We'll be able to test Einstein's theory of general relativity in the most extreme environments possible. We'll be able to use black hole mergers as standard sirens to measure the expansion rate of the universe, independent of other methods. The two galaxies in this James Webb study are still too far apart for their black holes to be close to merging. They might not even have encountered each other directly yet in the centers of the galaxies. But over the next few 100 million years, as the galaxies complete their merger, the black holes will spiral inward, shedding energy through gravitational interactions with stars and gas until they're close enough that gravitational waves take over and drive them together. That final merger will happen quickly. Once the black holes are within a few Schwarzschild radii of each other, a distance comparable to their own event horizons, the gravitational wave emission becomes so strong that they merge in a fraction of a second. The space-time around them ripples and distorts. The merged black hole rings like a bell, emitting gravitational waves that propagate outward at the speed of light, carrying information about what just happened to any detector that's listening. And then silence. A new, larger black hole sits at the center of the merged galaxy, surrounded by a disk of accreting gas that glows across the electromagnetic spectrum. An active galactic nucleus is born. For a few million years, the merged galaxy will be one of the brightest objects in the universe, powered not by stars, but by the gravitational energy of matter falling into the central black hole. We're seeing this process at various stages all across the universe. Quasars, those incredibly luminous beacons visible across billions of light years, are thought to be galaxies in the aftermath of major mergers, with supermassive black holes gorging on the gas funneled to the center by the collision. They represent a phase that most large galaxies probably go through at some point in their lives. Our Milky Way's central black hole, Sagittarius A-, is relatively quiet right now. It's not accreting much material, so it's not very luminous. But there's evidence that it was more active in the past, and it might become active again in the future, especially when we merge with Andromeda. The night sky of Earth, billions of years from now, might be lit by a quasar in our own galactic center. But I'm getting ahead of myself. Let's return to the bridge and think about what other observations would help us understand this system better. James Webb has given us incredible data, but it's not the only tool we have. Radio telescopes can observe the cold molecular gas, the raw material for star formation that James Webb's infrared eyes can't see directly. X-ray telescopes can find high-energy phenomena like supernova remnants and accreting black holes. Optical telescopes can measure the motions of stars and gas with exquisite precision. Multi-wavelength astronomy, observing the same object at many different wavelengths from radio to gamma rays, is how we get the complete picture. Each wavelength reveals different aspects of the physics. Infrared shows us dust and star formation. Optical and ultraviolet show us hot stars and ionized gas. Radio shows us cold molecules and magnetic fields. X-rays show us high-energy particles and extreme gravitational environments. Gamma rays show us the most energetic processes in the universe, cosmic ray interactions, and particle acceleration. For this system, follow-up observations with the Atacama Large Millimeter Array, or ALMA, would be invaluable. ALMA is a radio telescope array in Chile that can map the distribution of molecular gas, particularly carbon monoxide, which is a tracer of hydrogen molecules. Knowing where the molecular gas is, how dense it is, and how it's moving would tell us where future star formation will occur and how the gas is being channeled through the bridge. Similarly, observations with the Hubble Space Telescope could resolve individual star clusters in the bridge. James Webb has the sensitivity to see the diffuse emission, but Hubble's higher resolution in optical and ultraviolet light could pick out the brightest, hottest stars and clusters, giving us a census of the massive stellar population. And if we really want to understand the dynamics, we need three-dimensional information. We need to know not just where things are in the sky, but how they're moving in 3 dimensions. Radial velocities, the motions toward and away from us, we can get from spectroscopy. But transverse motions, the sideways movements across the sky, are harder. They require precise measurements of position over many years, waiting for stars to noticeably shift their locations due to their own motions. The Gaia spacecraft, which is mapping the positions and motions of over 1 billion stars in the Milky Way, has revolutionized our understanding of our own galaxy's structure and history. We need something like Gaia, but for external galaxies. A mission that can measure the precise positions and motions of stars in nearby galaxies, building up a 3-dimensional map of their structure and dynamics. Such a mission doesn't exist yet, and it would be technically challenging. The distances are so great that even fast-moving stars would take decades to show measurable position changes. But it's not impossible. With future technology, with bigger telescopes and better detectors, we might be able to do it. And when we do, we'll see galaxies not as static pictures, but as living, breathing, evolving systems, their stars moving through intricate paths shaped by gravity and history. The bridge between these two colliding galaxies would be a perfect target for such observations. Understanding the 3-dimensional flow of material through the bridge, seeing how stars and gas move from one galaxy to the other, watching the dynamics in action, would give us unprecedented insight into the mechanics of galaxy mergers. But even without that future technology, we can learn a lot from what we have. The James Webb data is a treasure trove that will be mined for years to come. There are features in the images that haven't been fully explained yet. Faint wisps of emission that might be outflows from star-forming regions. Knots of emission that don't have obvious counterparts in other wavelengths. Asymmetries in the structure that hint at complexities in the gravitational field. Each of these features is a clue. Each is a piece of the puzzle. Astronomy is detective work on a cosmic scale, and we're gathering evidence, building a case, trying to reconstruct events that happened millions of years ago and are still unfolding. One of the most exciting prospects is the possibility of finding planets in this bridge. We've found planets around stars in a wide variety of environments. Stars in dense clusters, stars in the galactic bulge, stars in the outskirts of the galaxy, even stars that are orbiting closely around the supermassive black hole at the Milky Way center. Planets are everywhere we look. Could there be planets in this tidal bridge? Stars are forming, so presumably planetary disks are forming around them. Whether those disks survive long enough to form planets, and whether any planets that do form remain in stable orbits, is an open question. The environment is harsh and dynamic, but life finds a way, as the saying goes, or at least planet formation finds a way. Detecting such planets would be incredibly difficult. The stars in the bridge are too distant for most planet hunting techniques. We can't use the transit method, watching for stars to dim as planets pass in front of them, because the stars are too faint. We can't use the radial velocity method, watching for stars to wobble due to orbiting planets, because the spectroscopic precision required is beyond current capabilities for such distant, faint stars. But maybe, just maybe, with next-generation instruments, we'll be able to do it. The Extremely Large Telescope, or ELT, being built in Chile, will have a mirror 39 meters across, dwarfing anything we have now. It will be able to directly image planets around nearby stars and take spectra of their atmospheres. It might just barely be able to detect the most massive planets around the brightest stars in this bridge. And if we find planets there, what then? Can we look for signs of life? Probably not at that distance. But we can characterize the planets, learn about their sizes, temperatures, atmospheres. We can add them to the growing census of exoplanets, the planets around other stars, and continue building our understanding of how common and diverse planetary systems are in the universe. Every planet is a world, a place with geography, with weather, with a unique history. Some are barren rocks, some are ice balls, some are gas giants with no solid surface, and some, maybe just maybe, have oceans and atmospheres and life. We don't know yet. We're only beginning to explore the diversity of planetary systems. But every new discovery brings us closer to answering the fundamental question. Are we alone? The bridge between these colliding galaxies is, in a cosmic sense, a laboratory for studying that question. It's a place where conditions are different from the norm, where the environment is in flux, where star and planet formation might proceed in ways we haven't considered. Studying such extreme environments helps us understand the range of possibilities, the full parameter space in which planets and life might arise. Now, I want to zoom out one more time and think about this discovery in the context of the universe's history. We're living in a special time, cosmically speaking. The universe is about 13.8 billion years old, and we're here in the middle of its lifespan, or maybe a bit past the middle depending on what happens with dark energy. The era of star formation is winding down. The universe's star formation rate peaked about 10 billion years ago and has been declining ever since. The gas reservoirs in galaxies are being depleted. Fewer mergers are happening now than in the past. The universe is, in a sense, aging, settling down. The wild, chaotic days of youth are over. But it's not over yet. Star formation is still happening. Galaxies are still merging. New stars are still being born. New planets are still forming, and new possibilities for life are still emerging. We're in the autumn of the universe's year, but autumn can be beautiful. The colors might be changing, but there's still vitality, still growth, still change. In the far future, trillions of years from now, star formation will cease entirely. All the gas will either be locked up in stars, white dwarfs, neutron stars, and black holes, or will be ejected from galaxies into the intergalactic medium where it's too diffuse to form new stars. The universe will be populated by aging stars, slowly fading away, until even they burn out and go dark. The last stars to shine will be the smallest red dwarfs, stars with only a tenth the mass of the Sun. They burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. Long after the Sun has exhausted its fuel and become a white dwarf, long after all the massive stars have exploded or collapsed into black holes, red dwarfs will still be glowing faintly in the darkness. And then, eventually, even they will die. The universe will enter an era called the degenerate era, dominated by dead stellar remnants, white dwarfs, neutron stars, and black holes. These objects will slowly evaporate via quantum processes, Hawking radiation and proton decay, over timescales so vast that they're hard to comprehend. 10 to the 35 years, 10 to the 40 years. Numbers so large that they dwarf the current age of the universe the way the age of the universe dwarfs a human lifetime. And finally, in the unimaginably distant future, even the black holes will evaporate, and the universe will be a thin soup of elementary particles, photons, and dark matter, expanding forever, cooling forever, approaching absolute zero but never quite reaching it. It's a bleak picture, and yet there's a strange beauty to it. The universe, having experimented with complexity, with structure, with stars and galaxies and life, will return to simplicity, to homogeneity, to equilibrium. It's the ultimate expression of entropy, the second law of thermodynamics playing out on the largest possible scale. But we're not there yet. We're here now, in the age of stars and planets, in the era when the universe is still capable of creating complexity and wonder. And discoveries like this bridge between colliding galaxies remind us of how much is still happening, how much is still being created, how much beauty and structure still emerges from the chaos. So what have we learned? What does this discovery mean? It means that star formation is more resilient, more adaptable, more creative than we thought. It means that the space between galaxies isn't empty, but filled with potential. It means that collisions and chaos can create as much as they destroy. It means that the universe is still full of surprises, still capable of showing us things we didn't expect, still teaching us that our models and theories are approximations, useful but incomplete. It means that James Webb is living up to its promise, that the investment, the decades of planning, the billion-dollar price tag, the risks and challenges of launching and deploying such a complex machine 1,000,000 miles from Earth were worth it. Because this telescope is showing us the universe in ways we've never seen before, revealing secrets hidden in infrared light, opening new windows on cosmic history. And it means that we're part of something larger. The atoms in our bodies were forged in processes like the ones we're observing in this bridge. The elements that make up our world, our technology, our bodies were created in stars, dispersed by supernovae, mixed and recycled through generations of stellar birth and death. We are, quite literally, the universe observing itself, matter organized in such a way that it can contemplate its own existence. That's what excites me about astronomy. It's not just the pretty pictures, though those are wonderful. It's not just the intellectual challenge, though that's stimulating. It's the connection, the realization that we're not separate from the cosmos, looking at it from the outside. We're part of it, made of it, shaped by it, and capable of understanding it. Every time we point a telescope at the sky and discover something new, we're expanding the boundaries of human knowledge. We're pushing back the darkness of ignorance. We're writing a new chapter in the story that began with the first humans who looked up at the stars and wondered what they were seeing. This bridge between colliding galaxies is one more chapter in that story. It's a reminder that the universe is vast beyond comprehension, ancient beyond imagination, and yet understandable through science, through observation, through careful thought and analysis. It's a reminder that we live in an amazing time, when technology allows us to see farther and more clearly than ever before, when discoveries that would have been impossible a generation ago are now routine. And it's a reminder to stay curious, to keep asking questions, to never assume we know everything, because every answer leads to new questions. Every discovery reveals new mysteries. The bridge between these galaxies has answered some questions about star formation and galactic evolution, but it's raised many more. How common are such structures? What role do they play in the overall story of galaxy growth? What happens to them in the long term? Can planets form there? Could life exist there? We don't know yet. We're still learning, still exploring, still discovering. And that's the most exciting thing of all. The universe is not a finished book we're reading. It's a story still being written, and we're fortunate enough to be here, now, participating in its creation, contributing our small part to the grand narrative of cosmic evolution. So the next time you look up at the night sky, remember this. Somewhere out there, for 100 million light years away, two galaxies are colliding, and in the space between them, stars are being born. Stars that might have planets. Planets that might have life. Life that might, someday, look up at their own sky and wonder if they're alone, just as we do. We are connected to those distant stars, to those potential worlds, by the laws of physics that operate everywhere in the universe, by the chemistry that creates atoms and molecules, by the light that travels across cosmic distances to bring us information, and by the curiosity that drives us to study and understand. We are the universe waking up, becoming aware of itself, exploring its own structure and history. And discoveries like this, strange bridges between colliding galaxies glowing with newborn stars, are part of that awakening. They're the universe looking at itself in the mirror and being surprised by what it sees. That's the message of James Webb's discovery. That's the takeaway. The cosmos is stranger, more beautiful, more dynamic, and more creative than we imagined. And we're only just beginning to understand it. But let's dig even deeper into what makes this discovery so revolutionary, because there are layers to this story that reveal fundamental truths about how the universe assembles its largest structures. The bridge isn't just a curiosity. It's a window into the hidden architecture of cosmic evolution. Think about the role of dark matter in all of this. We can't see dark matter directly. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all as far as we can tell. But we know it's there because of its gravitational effects. Galaxies rotate too fast to be held together by just the visible matter. Galaxy clusters have too much gravitational pull to be explained by stars and gas alone. The universe's large-scale structure, the cosmic web of filaments and voids, requires dark matter to form. Each of these galaxies is embedded in a massive dark matter halo, probably extending 10 times farther than the visible galaxy itself. These halos are what's really colliding first. Long before the stars and gas come close enough to interact, the dark matter halos have already begun to merge, their gravitational fields reaching out across millions of light years to pull and tug at each other. Computer simulations of galaxy collisions have to account for dark matter to get realistic results. When you run a simulation with only visible matter, the galaxies pass right through each other, barely affected. But add dark matter, and suddenly you get tidal tails, bridges, warped spiral arms, all the features we actually observe. The dark matter provides the gravitational scaffolding upon which the visible universe hangs. In the case of this bridge, the dark matter halos are playing a crucial role in determining where and how the gas flows. The bridge follows the path of least resistance through the combined gravitational potential of both halos. It's like water flowing downhill, except the hills are made of invisible matter and the water is hydrogen gas. The densest parts of the dark matter distribution create gravitational wells where gas accumulates, and those are precisely where we see the knots of star formation. We can actually map the dark matter distribution, not by seeing it directly, but by observing how it bends light from background galaxies. This technique, called gravitational lensing, uses Einstein's general relativity. Mass curves spacetime, and light follows the curvature of spacetime, so massive objects act as cosmic lenses, distorting and magnifying the images of objects behind them. For this particular system, detailed gravitational lensing studies haven't been done yet, but they will be. By measuring the distortions of hundreds or thousands of background galaxies visible around and behind the colliding pair, astronomers can reconstruct the three-dimensional distribution of mass, both visible and dark. That mass map will reveal the true structure of the collision, showing us where the dark matter is concentrated and how it's flowing. And here's something that might blow your mind. The dark matter particles in those halos aren't actually colliding with each other either. Remember, dark matter doesn't interact electromagnetically, but it also has very little self-interaction through other forces. So when two dark matter halos merge, the particles mostly pass right through each other, just like the stars do. They're affected by gravity, so their trajectories get bent, their orbits get scrambled, but they don't crash and stick together. This creates a fascinating situation where you have three different components of the galaxies all behaving differently during a collision. The stars pass through each other like ghosts. The gas slams together and creates shock waves. And the dark matter also passes through but gets gravitationally mixed and merged. Each component has its own story, its own dynamics, and understanding the full picture requires tracking all three. The James Webb observations are primarily showing us the gas component, specifically the star-forming regions in the bridge. But that's just one piece of a much larger puzzle. The full understanding requires combining data from multiple wavelengths and multiple techniques: optical and infrared for stars and gas, radio for cold molecular gas, X-ray for hot gas and energetic processes, and gravitational lensing for dark matter. Now let's talk about something that's been bugging astronomers since this discovery was announced: the energy budget. Where is all the energy coming from to power this star formation? Star formation requires energy input to compress gas to the point where it can collapse under its own gravity. In normal galactic disks, this energy comes from several sources: spiral density waves, rotating patterns that compress gas as it flows through them, supernova explosions that trigger new star formation in neighboring clouds, gravitational instabilities in the disk itself. All of these mechanisms require the organized structure of a galactic disk to operate efficiently. The bridge has none of that structure. It's a stream, not a disk, and yet it's forming stars at a prodigious rate. So where's the energy coming from? The collision itself is the most obvious source. When two galaxies come close enough for their gravitational fields to interact strongly, enormous amounts of gravitational potential energy are released. This energy goes into several places. Some of it accelerates gas and stars to high velocities. Some of it heats gas through shock waves. Some of it goes into tidal deformations, pulling material away from the galaxies. And some of it indirectly powers star formation by compressing gas clouds. But there's another, more subtle energy source that's often overlooked: magnetic fields. The interstellar medium isn't just gas. It's magnetized plasma, threaded with magnetic field lines that can store and release enormous amounts of energy. When gas flows through the bridge, it carries magnetic fields with it. As the gas gets compressed and stretched by the gravitational dynamics, the magnetic fields get amplified. Stronger magnetic fields mean higher magnetic pressure, which can help support gas clouds against gravitational collapse. But paradoxically, magnetic fields can also trigger collapse through processes like magnetic reconnection. Magnetic reconnection is what powers solar flares on the sun. Field lines get twisted and stressed, and then they snap and reconnect in a different configuration, releasing energy explosively. The same process happens in the interstellar medium, just on vastly larger scales. A single reconnection event in a molecular cloud can release enough energy to trigger the formation of an entire star cluster. James Webb can't observe magnetic fields directly, but radio telescopes can, by measuring the polarization of radio waves emitted by electrons spiraling around field lines. Follow-up observations with facilities like the Very Large Array or the Square Kilometre Array could map the magnetic field structure in this bridge and test whether magnetic reconnection is playing a role in the star formation. There's also the question of turbulence. The gas in the bridge isn't flowing smoothly. It's turbulent, with eddies and vortices and shock fronts creating a complex, chaotic flow pattern. Turbulence is a double-edged sword for star formation. On one hand, it can prevent collapse by providing additional pressure support. On the other hand, turbulent compression can create dense knots that become gravitationally unstable. The balance between these effects determines whether turbulence helps or hinders star formation, and that balance depends on the Mach number, the ratio of the gas velocity to the sound speed. In the bridge, the velocities are high, hundreds of kilometers per second in some regions, and the temperature is also high, which increases the sound speed. The Mach number is probably in the range of 10 to 30, indicating highly supersonic turbulence. At such high Mach numbers, turbulence creates a wide range of densities, from very low-density voids to very high-density filaments and clumps. It's in those high-density regions that star formation can occur despite the overall low average density of the bridge. The turbulence is effectively pre-processing the gas, sorting it into regions that can and cannot form stars. This is a key insight from modern star formation theory. It's not just about having a certain average density. It's about having structure, having a distribution of densities with some regions dense enough to collapse. Turbulence creates that structure naturally through a process called hierarchical fragmentation, where large gas clouds break up into smaller clouds, which break up into even smaller clouds, down to the scale of individual star-forming cores. The bridge between these colliding galaxies is a laboratory for studying this process in an extreme environment. The turbulence is stronger than in a normal galactic disk. The magnetic fields are different. The radiation field is harsher. And yet, star formation is happening. By comparing the star formation in the bridge to star formation in more normal environments, we can test our theories and refine our understanding of what's truly necessary for stars to form. Let me shift gears and talk about what this discovery means for our understanding of chemical evolution across cosmic history. I mentioned earlier that the metallicity in the bridge is surprisingly high, but let's unpack what that really means for the grand narrative of cosmic chemical enrichment. When the universe was young, in the first few 100 million years after the Big Bang, there were no heavy elements. 0. The first stars, called population 3 stars, formed from pristine primordial gas that was essentially just hydrogen and helium with trace amounts of lithium. These stars were probably very massive, hundreds of times the mass of the Sun, burning furiously hot and bright, living for only a few million years before exploding as parent stability supernovae that completely destroyed the star, leaving no remnant. Those explosions seeded the universe with the first heavy elements. Carbon, oxygen, silicon, iron, all created in the nuclear furnaces of those first stars and their supernova deaths. The next generation of stars, population 2 stars, formed from gas that had been modestly enriched by population 3 supernovae. And then the next generation, population 1 stars like our Sun, formed from even more enriched material. This process of progressive enrichment is ongoing. Every generation of stars increases the heavy element abundance. Every supernova adds to the cosmic inventory of metals. Over billions of years, the average metallicity of the universe has been steadily climbing. But the rate of enrichment isn't uniform. Some regions enrich faster than others. Galaxy centers, where star formation is intense and supernova rates are high, enrich quickly. Galactic outskirts, where star formation is sparse, enrich slowly. And different types of environments enrich at different rates depending on how efficiently they retain the heavy elements ejected by dying stars versus losing them to winds and outflows. The high metallicity in the bridge tells us that this material has been through many cycles of star formation and enrichment. It's not pristine outer disk gas. It's processed inner disk gas that's been pulled out by the tidal forces of the collision. This has implications for understanding how galaxy mergers redistribute metals, mixing material from different parts of the galaxies and potentially altering the chemical evolution of the merged system. There's also the question of what happens to the metals created in the bridge itself. The massive stars forming there will enrich the local gas when they explode as supernovae in a few million years. Will those metals stay in the bridge, further enriching it? Or will they be blown out by supernova winds and dispersed into the intergalactic medium? Or will they eventually fall back into one of the galaxies, contributing to future star formation there? The answer depends on the energetics of the supernovae and the gravitational potential of the system. If the supernova explosions are energetic enough, and if the bridge is gravitationally shallow enough, the metals could escape entirely. This process, called galactic winds or supernova-driven outflows, is a major mechanism for enriching the intergalactic medium with heavy elements. In fact, one of the major puzzles in astrophysics is the missing metals problem. When we add up all the metals in stars and gas in galaxies, we don't find as much as we expect based on the total star formation history of those galaxies. A significant fraction of the metals produced by stars seem to have disappeared, and the leading explanation is that they've been blown out into the intergalactic medium by winds and outflows. The bridge could be a site where this process is happening in real time. Stars form, quickly enrich the local environment, explode, and blow their metals out into intergalactic space. If so, then structures like this bridge might be important contributors to the intergalactic metal budget, enriching the space between galaxies and seeding future generations of galaxies with the raw materials for planets and potentially life. This brings us to a fascinating thought experiment. If planets form in the bridge, and if some fraction of the metals from supernovae in the bridge escape into intergalactic space, then billions of years from now, those metals might become part of a new galaxy forming elsewhere in the universe. And that new galaxy might form stars and planets using materials that were once part of this bridge. It's the ultimate form of recycling. Atoms that were once in a tidal bridge between colliding galaxies, billions of light years away, could eventually end up in another planet orbiting another star in another galaxy, perhaps hosting another civilization wondering about their own cosmic origins. The universe doesn't waste anything. Every atom gets used and reused in an endless cycle of creation and destruction. Now, let's consider the observational challenges that the James Webb team had to overcome to study this system. Observing distant galaxies isn't just pointing a telescope and taking a picture. It's a complex process that requires careful planning, precise execution, and sophisticated data analysis. First, there's the scheduling. James Webb is the most oversubscribed telescope in history. For every hour of observing time available, there are many hours worth of proposals from astronomers around the world who want to use it. The competition for time is fierce. The team that proposed observing this system had to make a compelling scientific case, explaining why their observations were important and couldn't be done with any other telescope. They succeeded, obviously. Their proposal was approved and they were allocated time. But even then, the observations had to be carefully designed. Which instruments to use? Which filters? How long to expose? What dithering pattern to use to fill in the gaps between the mirror segments and detector chips? Every choice involves trade-offs. Longer exposures mean better sensitivity, but fewer targets can be observed in a given amount of time. Narrower filters provide better spectral resolution but capture less light. Pointing at one part of the sky means not pointing at another. Telescope time is precious, and every second counts. For this particular observation, the team used a combination of imaging and spectroscopy. Broadband imaging with multiple filters to capture the overall structure and identify regions of interest. Narrowband imaging to isolate specific emission lines like hydrogen alpha and oxygen 3. And spectroscopy with the NIR-SPEC instrument to get detailed spectra of selected regions in the bridge. The data came down from the telescope as raw numbers, digital counts from the detector pixels. Converting those numbers into scientific images and spectra requires a complex calibration pipeline. You have to correct for the detector's response, remove instrumental artifacts, subtract the sky background, account for the telescope's point spread function, and many other steps. The James Webb pipeline is largely automated, but it's not perfect. Astronomers still have to examine the data carefully, looking for problems, applying additional corrections, making decisions about how to handle edge cases. It's painstaking work, but necessary to ensure the data is as accurate as possible. And then comes the analysis, measuring the brightness of regions in different filters, extracting spectra and identifying emission lines, fitting models to the data to determine physical parameters like temperature, density, and chemical composition, comparing the observations to theoretical predictions and numerical simulations. This is where the science really happens. This is where observations become understanding. And it requires expertise in astrophysics, statistics, computer science, and often a bit of intuition and creativity. The data doesn't come with an instruction manual saying, "Here's what you're looking at." You have to interpret it, make inferences, test hypotheses, and build a coherent picture from fragmentary evidence. The team analyzing this bridge has done exceptional work. They've extracted from the data not just pretty pictures, but quantitative measurements of star formation rates, gas masses, metallicities, velocities, and more. They've compared their findings to other colliding galaxy systems. They've run simulations to test whether the observations match theoretical predictions. And they've written papers describing their results, adding to the collective knowledge of the astronomical community. But their work isn't done. This is just the first analysis of this system. There will be follow-up studies, reanalysis with improved techniques, comparison with data from other telescopes. Science is an iterative process. Each study builds on previous work, refining our understanding, correcting mistakes, adding new pieces to the puzzle. And that's how it should be. Science doesn't claim to have all the answers. It's a method for approaching truth, not a collection of facts written in stone. We make our best interpretations based on available evidence, and we remain open to revising those interpretations as new evidence comes in. In the case of this bridge, there's still much we don't know. We don't know the exact three-dimensional geometry of the system. We don't know the orbital history of the two galaxies. We don't know the fate of the bridge in the long term. We don't know if there are planets forming there. We don't know if the star formation will continue or shut down as conditions change. But we're learning. With every observation, with every analysis, with every simulation, we learn more. We constrain the possibilities. We rule out some explanations and support others. We build a more complete, more accurate, more nuanced understanding of how the universe works. Let's zoom out one final time and consider this discovery in the broadest possible context. What does it tell us about our place in the cosmos? What does it mean for humanity, for our understanding of ourselves and our origins? We are, as I've said, made of star stuff. Every atom in your body was forged in processes like those occurring in this bridge. Hydrogen fused into helium in stellar cores. Helium fused into carbon and oxygen. Carbon and oxygen fused into heavier elements. And when those stars died, they scattered their atomic ashes into space, where they mixed with primordial hydrogen, collapsed into new stars, and eventually found their way into planets, into oceans, into the molecules of life, into you. This isn't metaphor. This is literal history. The calcium in your bones was created in a supernova explosion billions of years ago. The iron in your blood was synthesized in the core of a massive star. The oxygen you breathe was forged in the nuclear furnace of a star that died before the sun was born. You are, quite literally, the universe-made conscious matter arranged in such a way that it can contemplate its own existence and origins. And here's the profound part. You're not special in this regard. Everything around you, every person, every animal, every plant, every rock and raindrop and grain of sand, is made of the same cosmic material, forged in the same stellar crucibles, following the same laws of physics. We are all stardust. We are all connected by our shared atomic ancestry. This connection goes beyond Earth, beyond our solar system, beyond our galaxy. The atoms in the bridge between those colliding galaxies, 400 million light-years away, are cousins to the atoms in your body. They followed a different path through space and time, but they share the same ultimate origin in the Big Bang, the same journey through stellar interiors, the same alchemy of nuclear fusion that transmuted simple elements into complex ones. When you look at an image of that bridge, you're not looking at something alien and separate. You're looking at family. Distant family, to be sure, separated by unimaginable distances and timescales, but family nonetheless. We are all part of the same cosmic story, all participants in the same grand experiment in structure and complexity that began 13.8 billion years ago and continues to this day. This perspective, this cosmic perspective, has the power to transform how we see ourselves and our world. When you realize that national boundaries are invisible from space, that all of humanity occupies a pale blue dot suspended in a sunbeam, as Carl Sagan put it, petty differences seem less important. When you understand that we are all made of the same atoms, created in the same processes, sharing the same origins, divisions based on race or nationality or religion seem arbitrary and meaningless. We are one species on one planet orbiting one star in one galaxy in a universe of 2 trillion galaxies. We are incredibly rare, if not unique, in our ability to understand and appreciate this cosmic context. We are the universe's way of knowing itself, the mechanism by which atoms can contemplate atoms, by which the cosmos can explore its own structure and history. This is a responsibility as much as a privilege. We have the capability to understand, and therefore we have the obligation to use that understanding wisely, to preserve the conditions that allow life and consciousness to exist, to explore and learn and grow, to look outward at the cosmos with wonder and inward at ourselves with humility. The bridge between those colliding galaxies teaches us about resilience and creativity, about how order emerges from chaos, how beauty arises from violence, how life, or at least the conditions for life, persist even in the most unlikely places. Stars forming where they shouldn't be able to form, structure appearing where we expected only randomness. The universe finding a way to create complexity despite entropy's relentless push toward disorder. If stars can form in a tidal bridge between colliding galaxies, what else is possible? What other surprises await us in the cosmos? What other forms of structure, of organization, of complexity might exist in environments we haven't yet explored or even imagined? The universe is 13.8 billion years old and 93 billion light-years across. We've explored a tiny fraction of it in any detail. We've seen amazing things, strange things, beautiful things, but there's so much more out there waiting to be discovered. Every galaxy we observe in detail reveals new mysteries. Every star system we study shows unexpected diversity. Every planet we characterize challenges our assumptions about what planets can be like. And we've only just begun. James Webb has been operating for a couple of years. It's designed to last at least 10 years, possibly 20 with careful fuel management. In that time, it will observe thousands of objects across the universe, from planets in our own solar system to the most distant galaxies visible, formed in the first billion years after the Big Bang. Each observation will tell a story. Each image will reveal secrets. Each spectrum will contain clues to how the universe works. And astronomers will spend years analyzing that data, extracting every bit of information, building models, testing theories, publishing papers, arguing over interpretations, and gradually, incrementally expanding our understanding. Beyond James Webb, there are other missions in the works. The Nancy Grace Roman Space Telescope, designed to survey vast areas of sky and study dark energy. The European Space Agency's Euclid mission, mapping the large-scale structure of the universe. Ground-based projects like the Extremely Large Telescope, the Giant Magellan Telescope, and the 30-meter telescope, each with mirrors larger than anything currently in operation. And in the more distant future, truly ambitious projects. Space telescopes larger than James Webb, assembled in orbit from components launched separately. Interferometers with multiple spacecraft flying in formation, acting as a single telescope with an effective aperture hundreds or thousands of kilometers across. Direct imaging of Earth-like planets around nearby stars, looking for signs of life in their atmospheres. These future missions will build on what James Webb is teaching us. They'll follow up on discoveries, test new hypotheses, explore in even greater depth. The bridge between these colliding galaxies is just one of countless objects that will be studied over the coming decades, each contributing its piece to the larger puzzle. And through it all, the fundamental questions remain. How did the universe begin? How did galaxies form? How do stars and planets come into being? What is dark matter? What is dark energy? Is there life elsewhere in the cosmos? Are we alone? We don't have all the answers yet. We may never have all the answers, but we keep looking, keep exploring, keep questioning, because that's what humans do. We're curious. We're explorers. We're scientists and dreamers, engineers and poets, mathematicians and artists. We build telescopes and spacecraft to extend our senses beyond Earth, to see things our ancestors couldn't have imagined, to touch, however indirectly, the farthest reaches of space and time. The bridge between those colliding galaxies, glowing with newborn stars 400 million light-years away, is a reminder of why we do this. Not for practical applications, though those often emerge unexpectedly from basic research. Not for economic benefit, though the technology developed for space exploration has countless terrestrial uses. But for understanding, for knowledge, for the sheer joy of discovery. Because when you see something like this bridge, something that challenges your assumptions and expands your conception of what's possible, it changes you. It makes you see the world differently. It reminds you that the universe is bigger, stranger, more wonderful than everyday experience suggests. It lifts your gaze from the mundane concerns of daily life to the grand sweep of cosmic evolution. And that's valuable. That's important. Not in a dollars and cents way, but in a deeper sense. Understanding our place in the universe, knowing where we came from and where we're going, appreciating the beauty and complexity of nature on all scales from quarks to galaxy clusters. These things make us more fully human. They satisfy a deep need, a drive that's as fundamental to our nature as the need for food or shelter or companionship. We are meaning-seeking creatures. We want to understand. We want to know the story of which we're a part. And science, astronomy in particular, provides that story. It gives us a narrative that's true, as far as we can tell, based on evidence rather than wishful thinking or ancient tradition. It's a story that's still being written, with new chapters being added constantly, and we're the authors, collectively writing the tale of cosmic history through our observations and theories and discoveries. The bridge between those colliding galaxies is one paragraph in that story. An important paragraph, revealing new information, raising new questions, pointing the way toward future explorations. But just one paragraph. There are billions more waiting to be written, trillions of objects waiting to be observed, countless phenomena waiting to be understood. And that's exciting. That's what makes this field so thrilling, so addictive for those of us who work in it. There's always something new to discover, always another mystery to solve, always another observation that doesn't quite fit the models and forces us to rethink our assumptions. The universe doesn't hand us easy answers. It makes us work for them. It challenges us, surprises us, humbles us. But it also rewards us with insights and beauty and a sense of connection to something vast and ancient and ongoing. So here we are in October 2025, looking at data from the James Webb Space Telescope showing star formation in a tidal bridge between two colliding galaxies. A specific discovery, a particular observation, one among thousands that James Webb will make during its lifetime. But also something more, a reminder of our cosmic heritage, a demonstration of the universe's creativity, a challenge to our understanding, a prompt to keep exploring, keep questioning, keep wondering, because that's what science is ultimately. It's organized curiosity, it's systematic wonder, it's the collective effort of humanity to understand the reality we inhabit. And discoveries like this, strange bridges glowing with newborn stars in the space between colliding galaxies, are the rewards of that effort. They're the treasures we find when we dare to look beyond the familiar, beyond the comfortable, beyond the limits of unaided human perception. We built James Webb to see these treasures. We invested decades of planning, billions of dollars, countless hours of human ingenuity and effort. And it's paying off, not just in this one discovery, but in hundreds of discoveries, each adding to our knowledge, each answering old questions and raising new ones, each piece contributing to the grand mosaic of cosmic understanding. This is the power of science. This is the value of exploration. This is why we reach for the stars even knowing we'll never touch them, why we peer into the depths of space and time, even knowing we'll never travel there, why we ask questions about the nature of reality, even knowing some answers may forever elude us. Because the asking matters, the searching matters, the wondering and questioning and exploring matter. They make us human. They connect us to every human who has ever looked up at the night sky and felt the pull of the infinite. They link us across time to our ancestors who first wondered what those points of light were, and forward in time to our descendants who will continue the exploration we've begun. The bridge between two colliding galaxies, 400 million light-years away, blazing with the light of newborn stars that will never be seen by human eyes except as patterns of light on a detector, converted to numbers, processed by computers, rendered as images on screens. That bridge is family. It's home. It's us. Because we are all stardust, and that bridge is making more stardust, continuing the cycle that made us possible, ensuring that the universe remains a place where matter can organize into complexity, where atoms can contemplate atoms, where consciousness can emerge and look back at its own origins with understanding and wonder. That's the final message. That's the conclusion. We are not separate from the universe. We are not observers standing outside, looking in. We are part of it, made of it, shaped by it. And when we study the cosmos, when we point our telescopes at distant galaxies and analyze their light, we are, in a very real sense, the universe studying itself. The bridge between those colliding galaxies is a mirror. When we look at it, we see ourselves, our history, our future. We see the processes that made us possible. We see the ongoing creativity of the cosmos. We see that we are temporary arrangements of matter, yes, but also that we are participants in something grand and beautiful and meaningful. And perhaps that's enough. Perhaps that's all the meaning we need. to be part of the universe's great experiment in complexity, to be the part that can understand, even if only partially, even if only temporarily, to be the mechanism by which the cosmos knows itself. The stars in that bridge will burn for millions or billions of years. Some will explode as supernovae. Some will quietly fade away. The bridge itself will eventually be incorporated into the merged galaxy. The atoms that make it up will continue their journey through space and time, being incorporated into new stars, new planets, perhaps new forms of life we can't imagine. And we'll be watching, or rather, our descendants will be watching with telescopes we haven't built yet, using techniques we haven't invented yet, asking questions we haven't thought of yet. Because the story continues, the exploration continues, the search for understanding continues. That's what makes us human. That's what makes us special, if anything does. Not our strength or our speed or our longevity, but our curiosity, our drive to understand, our willingness to invest enormous resources in building machines that extend our senses across the cosmos, just so we can know what's out there. The James Webb Space Telescope, sitting at the L2 point a million miles from Earth, cold and silent except for the faint whir of reaction wheels and the occasional firing of thrusters, is humanity's emissary to the universe. It's our eye in the sky, our window on infinity. And when it looks at something like this bridge between colliding galaxies and sends that data back to Earth, it's giving us a gift. The gift of knowledge, the gift of perspective, the gift of wonder. We should cherish that gift. We should treasure it. Not just the specific facts about star formation rates and metallicities and gravitational dynamics, though those are valuable, but the deeper truth that the gift represents. That we live in a universe of immense beauty and complexity, that we are capable of understanding that universe, and that the act of understanding connects us to something larger than ourselves. So look up at the night sky tonight. Know that somewhere out there, invisible to your eyes but visible to our telescopes, galaxies are colliding, stars are being born, atoms are being forged in nuclear fires. Know that those processes made you possible. Know that you are part of it all, not separate, not isolated, but deeply, fundamentally connected to the cosmos. And know that we're still learning, still discovering, still being surprised, still finding bridges of stars where we didn't expect them, still uncovering mysteries in the darkness, still writing new chapters in the story of cosmic evolution. This is the age of discovery. This is the era when humanity finally developed the tools to study the universe in unprecedented detail. And we're living through it. We're witnessing it. We're part of it. The bridge between those colliding galaxies, strange and unexpected and beautiful, is one more reminder that the universe still has surprises for us, that our journey of discovery is far from over, that the cosmos is an endless source of wonder, waiting for us to explore. And so we will. We'll keep building telescopes. We'll keep analyzing data. We'll keep asking questions. We'll keep searching for answers, because that's what we do. That's who we are. We are the universe awakened to itself. We are stardust contemplating stars. We are matter pondering matter. We are the cosmos exploring the cosmos. And in that exploration, in that endless quest for understanding, we find not just knowledge, but meaning. Not just facts, but purpose. Not just information, but inspiration. The bridge between two colliding galaxies, 400 million light-years away, glowing with the light of newborn stars that James Webb has captured and delivered to us, is more than a scientific curiosity. It's a message from the universe, a reminder of where we came from, what we're made of, and what we're part of. It's a mirror showing us ourselves. It's a window showing us infinity. It's a bridge, not just between galaxies, but between past and future, between ignorance and understanding, between isolation and connection. And it's beautiful, complex, mysterious, wonderful, just like the universe itself, just like us. But there's more to this story, layers upon layers that deserve exploration. Let's talk about what makes this particular collision system different from the hundreds of other merging galaxies we've observed over the decades. Because not all galaxy collisions are created equal, and this one has characteristics that make it especially valuable for understanding galactic evolution. The velocity of approach matters enormously. When two galaxies collide slowly, at relative speeds of just a few hundred kilometers per second, they have time to interact gradually. The collision is almost gentle by cosmic standards. Gas clouds compress slowly, star formation ramps up over millions of years, and the merger proceeds in a stately, almost predictable fashion. But when galaxies collide at high speed, thousands of kilometers per second, it's different. It's violent. The interaction time is short. Gas doesn't have time to settle into new equilibrium configurations before being disrupted again. Shock waves are more powerful. The compression is more sudden, and the resulting star formation can be explosive, brief, and intense. This system appears to be somewhere in the middle. The relative velocity is moderate, around 800 to 1,000 kilometers per second based on spectroscopic measurements. Fast enough to create dramatic effects, slow enough to allow extended structures like the bridge to form and persist. It's the Goldilocks zone of galaxy collisions, not too fast, not too slow, but just right for creating interesting astrophysics. The mass ratio between the two galaxies also matters. When a large galaxy collides with a much smaller one, we call it minor merger. The small galaxy gets shredded and absorbed, contributing its stars and gas to the larger galaxy, but not fundamentally altering its structure. The Milky Way has undergone many minor mergers over its history, swallowing dwarf galaxies and incorporating their material. But when two galaxies of similar mass collide, it's a major merger. Neither galaxy dominates. Both are transformed. The result is something entirely new, a merged galaxy that bears little resemblance to either progenitor. This is what will happen when the Milky Way and Andromeda collide. The system observed by James Webb appears to be a major merger. The two galaxies have comparable masses, each containing hundreds of billions of solar masses of stars and gas. They're wrestling each other, two titans locked in combat, and neither will emerge unchanged. The orientation of the collision affects what we see. If we're viewing the collision face-on, we see the full extent of tidal features, bridges and tails stretching across the sky. If we're viewing it edge-on, those same features are compressed along our line of sight, harder to distinguish from the galaxies themselves. The orientation also affects how much dust obscures our view, whether we're looking through the full thickness of dusty gas or seeing the system from a clearer angle. For this system, the orientation is favorable. We're viewing it at an oblique angle, neither perfectly face-on nor perfectly edge-on. This gives us a good three-dimensional perspective on the structure while not burying everything behind dust. It's another piece of cosmic luck that makes this system particularly valuable for study. Now let's discuss something that hasn't been emphasized enough: the sheer timescales involved in what we're observing. When you look at an image from James Webb, you're seeing a single moment frozen in time. But that moment represents just one frame in a movie that's been playing for hundreds of millions of years and will continue for hundreds of millions more. The light we see left those galaxies 400 million years ago. At that time on Earth, the first plants were just beginning to colonize land. Fish dominated the oceans, but there were no amphibians, no reptiles, no dinosaurs, no mammals, no humans. The entire age of complex life on land, from the first lungfish crawling onto mudflats to the development of human civilization, has occurred during the time it took that light to reach us. And the collision itself operates on similar timescales. The first close approach between these galaxies probably happened 100 million years or more before the moment captured in the James Webb image. The final merger won't be complete for another few hundred million years. If we could make a time-lapse movie of the entire event, with each frame separated by 1,000,000 years, it would take thousands of frames to show the full story. We can approximate such a movie using computer simulations. Astronomers input the properties of the two galaxies, their masses, sizes, gas content, dark matter halos, their initial positions and velocities. Then they let physics take over, running the simulation forward in time, watching as gravity sculpts the galaxies, pulls out tidal features, triggers star formation, and ultimately merges them into one. These simulations are remarkable achievements of computational astrophysics. They track millions or even billions of particles, each representing a parcel of stars or gas or dark matter. They calculate gravitational forces, gas dynamics, star formation, stellar feedback, black hole accretion, everything that affects galactic evolution. Modern simulations can run on supercomputers for weeks or months, producing terabytes of data that capture the collision in exquisite detail. By comparing simulations to observations, we can work backward to reconstruct the history of the system. We can figure out what the galaxies looked like before they collided, what their orbits were, when the first passage occurred, how many times they've interacted. This cosmic archaeology, piecing together the past from present-day evidence. For this particular system, preliminary simulations suggest the galaxies have completed at least one close passage and are now approaching for a second encounter. The bridge was formed during the first passage, when tidal forces reached out and pulled gas from both galaxies. That was probably 50 to 100 million years ago. Since then, the galaxies have swung apart on their elongated orbits, reached maximum separation, and are now falling back together. The next passage will be closer, more violent. More gas will be funneled to the galactic centers. The star formation rate will spike. The bridges and tails will be stretched and reconfigured. And after a few more passages, spread over another few 100 million years, the galaxies will finally lose enough orbital energy to merge completely, settling into a single elliptical galaxy. This brings us to an interesting question that's been debated in the astronomical community. What happens to spiral structure during a merger? Both of these galaxies appear to have been spirals before the collision began. You can still see hints of spiral arms in the James Webb images, though they're distorted and disrupted by tidal forces. Spiral arms are density waves, patterns that rotate through galactic disks, compressing gas and triggering star formation as the gas flows through them. They're sustained by the organized rotation of the disk and the balance between gravity and angular momentum. But in a merger, all that organization gets destroyed. The disks get warped, tilted, eventually completely scrambled. The spiral pattern breaks down. Most astronomers believe that major mergers of spiral galaxies produce elliptical galaxies. The evidence for this is strong. Elliptical galaxies are common in dense galaxy clusters where mergers are frequent, and rare in isolated environments where galaxies evolve undisturbed. The stars in elliptical galaxies are on random orbits rather than organized rotation, consistent with what you'd expect if they came from scrambled spiral disks. But there are complications. Some mergers might produce new spiral galaxies if there's enough gas left over after the initial starburst to settle back into a disk. Some elliptical galaxies might form through other mechanisms, like repeated minor mergers rather than one major collision. And some galaxies, called S0 or lenticular galaxies, have properties intermediate between spirals and ellipticals, with disks but no spiral arms, and their formation history is still debated. The system we're looking at will almost certainly become an elliptical. The gas content is high enough that a major starburst will consume most of it during the merger. What remains will be too turbulent and dispersed to settle into a new disk. The final galaxy will be a smooth, featureless ellipsoid of old red stars, its spiral heritage erased by the violence of collision. But that's hundreds of millions of years in the future. Right now, in the snapshot captured by James Webb, the system is still full of life and activity. Stars are forming. Spiral arms still exist in the less disturbed regions. The bridge glows with young, hot stars. It's a moment of transition, caught between the ordered past and the chaotic future. Let me shift to something more technical but absolutely crucial for understanding this discovery: the spectroscopic data. When James Webb observes an object, it doesn't just take pretty pictures. It also spreads the light into spectra, breaking it down by wavelength, revealing the fingerprints of different atoms and molecules. Every element has a unique spectral signature. Hydrogen emits light at specific wavelengths when its electrons jump between energy levels. So does helium, carbon, oxygen, nitrogen, iron, every element on the periodic table. By measuring which wavelengths are present and how bright they are, we can determine what the gas is made of, how hot it is, how dense it is, and how fast it's moving. The spectra from the bridge show strong emission lines from hydrogen, particularly the Balmer series, hydrogen alpha, hydrogen beta, and so on. This tells us the gas is ionized, stripped of electrons by intense ultraviolet radiation from hot stars. The ratios of different hydrogen lines tell us about the temperature and density of the gas. There are also strong lines from ionized oxygen, particularly doubly ionized oxygen called O3. These lines are classic signatures of HII regions, stellar nurseries where massive stars are ionizing the surrounding gas. The brightness of these lines, compared to the hydrogen lines, tells us about the metallicity and the ionization state. Nitrogen lines are present but weaker. The nitrogen to oxygen ratio is a sensitive indicator of the chemical enrichment history. Nitrogen is primarily produced in intermediate mass stars and released gradually over long timescales, while oxygen is produced in massive stars and released quickly in supernovae. A high nitrogen to oxygen ratio suggests a long history of star formation, while a low ratio suggests younger stellar populations. In the bridge, the nitrogen to oxygen ratio is moderate, consistent with gas that's been through several generations of star formation but hasn't been processed as extensively as gas in galactic centers. This supports the idea that the bridge material came from the outer parts of the galaxies, though with some contribution from more enriched inner disk gas. There are also absorption lines in the spectra, dark features where light is being absorbed rather than emitted. These absorption lines come from stars rather than gas. By analyzing the pattern of absorption lines, we can determine what types of stars are present, their ages, their metallicities, their temperatures. The stellar population in the bridge is mixed. There are very young stars, less than 10 million years old, showing strong absorption from hydrogen and helium and weak absorption from metals. There are middle-aged stars, tens to hundreds of millions of years old, showing stronger metal lines. And there might be older stars pulled from the galaxies themselves, though they're harder to detect because they're fainter than the young, luminous stars. This mixed stellar population tells a story of episodic star formation. The bridge hasn't been forming stars continuously at a constant rate. Instead, it's experienced bursts, periods of intense star formation followed by quieter periods, followed by new bursts. This makes sense given the dynamics of the collision. Each close passage between the galaxies compresses gas in the bridge, triggering a new wave of star formation. The Doppler shifts of the spectral lines reveal the kinematics, the motions of gas and stars. Lines that are shifted toward the blue are coming from material moving toward us. Lines shifted toward the red are coming from material moving away. The amount of shift tells us the velocity. In the bridge, the velocity field is complex. Some regions are moving toward one galaxy, some toward the other, some perpendicular to the bridge axis. There's turbulence, random motions with velocities of tens of kilometers per second. There's rotation, though it's not as organized as in galactic disks. And there's overall flow, material streaming along the bridge from one galaxy toward the other. This velocity structure contains information about the gravitational field, the mass distribution, the dynamics of the collision. By mapping the velocities in detail and comparing to simulations, we can constrain the masses of the galaxies, the inclinations of their orbits, even the distribution of dark matter in the system. One particularly interesting feature in the spectra is the width of the emission lines. Narrow lines indicate gas that's moving slowly or uniformly, with all the atoms having similar velocities. Broad lines indicate fast or turbulent motion, with atoms moving at a range of velocities along our line of sight, each contributing slightly Doppler-shifted light that adds up to a broadened line. In the bridge, some regions have narrow lines, suggesting relatively quiescent gas. Other regions have broad lines, indicating turbulence or organized flows. The broadest lines are found in regions where supernova feedback is strong, where the energy from exploding stars is stirring up the gas and driving fast outflows. These broad lines are evidence of stellar feedback in action. Young, massive stars don't just sit quietly and shine. They blow powerful stellar winds that push gas around. And when they explode as supernovae, they inject enormous amounts of energy into their surroundings, creating bubbles and shells of hot, fast-moving gas. This feedback is crucial for regulating star formation. Without it, galaxies would convert all their gas into stars very quickly, and the universe would look very different. Feedback provides a negative feedback loop, where star formation creates conditions that slow down or halt further star formation. It's one of the key processes that determines the efficiency of star formation and the properties of galaxies. In the bridge, feedback appears to be working but not dominant. Star formation is vigorous, but not so vigorous that it's blowing all the gas away. There's a balance, a steady state where new stars form, heat and stir the gas, but don't completely disrupt it. This balance won't last forever. As more massive stars form and explode, the feedback will strengthen, eventually dispersing much of the remaining gas and shutting down star formation in the bridge. Now let's talk about something that's absolutely fundamental but often overlooked: dust. Interstellar dust consists of tiny solid particles, much smaller than a grain of sand, made of silicates, carbon, and ice. Dust is incredibly important in astrophysics despite being such a small component of the interstellar medium by mass. Dust absorbs and scatters light, particularly blue and ultraviolet light. This is why dusty regions appear red, why the Milky Way has a dark band across it when viewed from Earth, why some galaxies are almost invisible in optical light but bright in infrared. Dust obscures our view, hiding much of the universe from optical telescopes. But dust also emits light, infrared light, thermal radiation from particles heated by starlight. When dust absorbs ultraviolet light from hot stars, it heats up to temperatures of a few tens of Kelvin, and at those temperatures it glows in the infrared. This re-emission is actually useful because it allows us to detect star formation even when it's hidden behind thick dust clouds. James Webb's infrared capabilities are perfect for studying dusty environments. Infrared light penetrates dust much better than optical light. Wavelengths of a few microns can pass through all but the densest dust clouds. This is why James Webb can see through the dust in star-forming regions and reveal the newborn stars within, something Hubble struggles with. In the bridge, dust is present but not overwhelming. The infrared colors indicate moderate dust extinction, enough to affect the observations but not enough to completely hide the star formation. This is actually somewhat surprising. You might expect a collision to kick up huge amounts of dust as molecular clouds are compressed and disrupted. But the bridge is more transparent than typical galactic disks. This could be because the bridge is less dense overall. Even though there are knots of star formation with high local densities, the average density of the bridge is lower than in galactic disks, so there's less dust per unit area along our line of sight. Or it could be that dust is being destroyed faster than it's being created, either by shocks that shatter grains or by the harsh radiation field that sublimates ice mantles and erodes grain surfaces. The dust in the bridge provides another chemical diagnostic. Dust grains contain a significant fraction of the heavy elements in the interstellar medium, particularly carbon, silicon, and iron. The amount of dust and its composition tell us about the chemical enrichment history and the balance between grain formation in stellar atmospheres and grain destruction in supernova shocks. Infrared spectroscopy can identify specific dust features. Silicate dust has characteristic absorption and emission features around 10 microns. Polycyclic aromatic hydrocarbons, or PAHs, complex carbon molecules, have features at several wavelengths in the mid-infrared. Ice mantles on grains produce absorption features in the near-infrared. The James Webb spectra show evidence for all of these components in the bridge. Silicate features indicating dust grains similar to those in the Milky Way. PAH features indicating the presence of these organic molecules, which are thought to be important in the chemistry that leads to the formation of more complex molecules and possibly to the building blocks of life. Ice features indicating cold regions where water ice has condensed onto grain surfaces. This chemical richness is encouraging if we're thinking about the potential for planet formation and life in the bridge. The molecular building blocks are there. The chemistry is active. If planets do form around stars in the bridge, they'll have access to all the complex organic chemistry necessary for life as we know it. Speaking of planets, let's think more carefully about what planetary systems in this environment would experience. I mentioned earlier that the radiation environment would be harsh, and it's worth unpacking what that means. Young, massive stars emit copious amounts of ultraviolet radiation. This radiation ionizes hydrogen, creating HII regions, but it also photodissociates molecules, breaking apart any complex chemistry that tries to form in the vicinity. And it photoevaporates protoplanetary disks, the dusty disks around young stars from which planets form. In a normal star-forming region like the Orion Nebula, massive stars can destroy protoplanetary disks around nearby lower-mass stars, preventing planet formation entirely or at least limiting the mass of planets that can form. This process is well documented in Orion and other nearby stellar nurseries. In the bridge, with its high star formation rate and numerous massive stars, this photoevaporation would be widespread. Any star forming near a cluster of massive stars would have its protoplanetary disk ablated away within a few million years, possibly before planets have time to form. But stars forming in more isolated regions of the bridge, far from the massive star clusters, might be protected. Their disks could survive long enough for planets to coalesce. It would be a matter of location, 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 just like in real estate but on a galactic scale. There's also the issue of dynamical perturbations. The bridge is not gravitationally stable. It's being pulled by two massive galaxies, stretched by tidal forces, buffeted by supernova explosions. Any planetary system that does form might not remain stable for long. Planetary orbits could be perturbed by passing stars or by the overall gravitational field of the bridge. Planets might be ejected from their systems, becoming free-floating rogues wandering through space. Or they might have their orbits become eccentric, plunging close to their host stars and then swinging far out, creating extreme seasonal variations. On the other hand, the bridge won't exist forever as a distinct structure. Eventually, it will be incorporated into the merged galaxy, and any planetary systems in it will become part of the stellar halo or outer disk of that galaxy. They might then enjoy billions of years of relative stability, long enough for life to evolve and develop. It's all speculation at this point. We have no direct evidence for planets in this bridge or any other tidal bridge. But the universe has shown us again and again that where there are stars, there are usually planets. And where there are planets, there's at least the potential for life. This brings me to one of the most profound implications of studying star formation in extreme environments like this bridge: understanding the full range of habitable environments in the universe. We've spent decades studying star formation in normal galactic disks because that's where we live, and it's the easiest to observe. But most of cosmic history has been dominated by mergers and interactions, by chaotic, violent events that look nothing like the peaceful Milky Way disk we inhabit. If we want to understand where life can arise in the universe, we need to understand star and planet formation in all environments, not just the calm ones. We need to know if planets form in tidal bridges, in galactic halos, in the outflows from active galactic nuclei, in dwarf galaxies, in globular clusters, everywhere stars form. Each environment has different challenges and different advantages for life. High radiation levels are bad, but high metallicity is good, providing more raw materials for rocky planets and complex chemistry. Dynamical instability is bad, but rich chemical environments are good. Isolation from other stars is bad for detecting technological civilizations, but good for avoiding sterilization events like nearby supernovae. The bridge we're studying is one data point in this cosmic census of habitable environments. By understanding the conditions there, we expand our knowledge of where to look for life and what kinds of planets and biospheres might exist in the universe. Let's shift gears and talk about the role of this discovery in the broader context of James Webb's mission and scientific legacy. James Webb wasn't built just to study one colliding galaxy system. It was built as a general-purpose observatory capable of addressing fundamental questions across all of astrophysics. Some of Webb's time is dedicated to deep surveys, staring at small patches of sky for hundreds of hours to detect the faintest, most distant galaxies. Other time goes to studying exoplanet atmospheres, looking for biosignatures in the air of alien worlds. Still, other time examines stars forming in our own galaxy, or planets in our solar system, or the structure of nearby galaxies. This collision system is part of Webb's program to study galaxy evolution, specifically how galaxies grow through mergers. There's a whole suite of observations of merging galaxies at different stages and different redshifts, building up a comprehensive picture of how this process works across cosmic time. By comparing nearby mergers like this one to distant mergers at high redshift, seen as they were billions of years ago, we can watch galaxy evolution happen. We can see how merger rates have changed over time, how star formation efficiency has evolved, how the availability of gas has decreased as the universe has aged. And by combining Webb's observations with data from other telescopes spanning the electromagnetic spectrum, we get a complete picture. Radio observations trace the cold molecular gas. Optical observations show the stellar populations. X-ray observations reveal the hot shocked gas and accreting black holes. Ultraviolet observations map the youngest, hottest stars. And infrared observations from Webb penetrate the dust to see everything in between. This multi-wavelength, multi-epoch, multi-target approach is how modern astrophysics works. No single observation tells the whole story. You need context, comparison, complementary data. You need to see objects at different times, in different conditions, across the full range of cosmic environments. The bridge between these two galaxies is one piece of a much larger mosaic. By itself, it's fascinating. In context, as part of the broader study of galaxy evolution, it's transformative. It's teaching us that star formation is more versatile than we thought, that tidal features are more than just passive debris, that the space between colliding galaxies is an active, dynamic, creative environment. Now let's consider the technological innovations that made this discovery possible, because the path from concept to execution for James Webb was anything but straightforward. The telescope was proposed in the 1990s, construction began in the 2000s, and it finally launched in 2021. Delays and cost overruns were common, and at several points the project nearly got canceled. Why so difficult? Because James Webb pushed the boundaries of what's possible in space technology. The segmented mirror, with its 18 hexagonal pieces, had to be designed to unfold in space and align to nanometer precision. The sun shield, 5 layers of Kapton film, each the size of a tennis court, had to be folded to fit in the rocket and then deploy perfectly in the vacuum of space. The instruments had to operate at cryogenic temperatures, 40 Kelvin or colder, achieved through passive cooling and specialized refrigerators for the mid-infrared instrument. The entire spacecraft had to be designed to last at least 10 years at the L2 point with no possibility of servicing or repair. Every component had to be tested exhaustively. Thermal cycling to simulate the temperature extremes of space. Vibration testing to ensure it could survive the rocket launch. Acoustic testing to verify it could withstand the sound levels during liftoff. Optical testing of the mirrors at cryogenic temperatures in vacuum chambers. Software testing of the complex autonomous deployment sequence. And then there was the launch itself and the deployment. Over 2 weeks, hundreds of mechanisms had to fire in the correct sequence. The sun shield had to unfold. The mirror segments had to swing into position. Instruments had to be powered on and checked out. If anything had gone wrong, the mission would have failed. But it all worked. The deployment was flawless. The mirrors aligned perfectly. The instruments came online and performed even better than specifications. It was a triumph of engineering, a testament to what humans can achieve when we work together toward a common goal. And the result has been a flood of discoveries. In just a few years of operations, James Webb has revolutionized multiple fields, found the most distant galaxies ever observed, detected complex molecules in exoplanet atmospheres, revealed the structure of star-forming regions in unprecedented detail, discovered new phenomena like this bridge that challenge our understanding. The discovery of vigorous star formation in the tidal bridge is exactly the kind of unexpected result that makes the investment in James Webb worthwhile. Yes, we wanted to answer specific questions about galaxy evolution and cosmic history, but we also we hoped, that Webb would show us things we hadn't predicted, phenomena we hadn't imagined, surprises that would force us to rethink our theories. This bridge delivers on that promise. It's not what anyone was specifically looking for, but it's exactly what we needed to find. A natural experiment testing star formation theory in extreme conditions. A window into processes that are common in the early universe but rare nearby. A reminder that the cosmos is more creative and diverse than our models capture. Let me address one more technical aspect that's crucial for interpreting the data: understanding what we're not seeing. Every observation has selection effects, biases that affect what we detect and what we miss. Being aware of these biases is essential for drawing correct conclusions. James Webb is incredibly sensitive, but it's not infinitely sensitive. Faint objects can escape detection. Regions of very low surface brightness might not stand out above the background noise. Stars embedded in extremely thick dust might remain hidden even from infrared eyes. The bridge we're seeing is the bright part, the regions where star formation is most vigorous, where the newest stars are ionizing the gas and making it glow. There might be a much more extended, fainter component of the bridge that we're not detecting, containing diffuse gas and older stars that don't emit strongly in the wavelengths Webb observes. There's also the issue of resolution. Webb's resolution, while excellent, is still finite. At the distance of these galaxies, each pixel in the image covers several hundred light-years. Structure smaller than that is blurred together, invisible to us. Individual star-forming regions, molecular clouds, even large star clusters might be unresolved, appearing as point sources or slightly fuzzy blobs. This means we're seeing the average properties of regions that might have considerable internal structure. A pixel that appears to show uniform star formation might actually contain a few dents not surrounded by much emptier space. A measurement of average metallicity might mask variations between different clouds with different enrichment histories. Higher resolution observations, either with future telescopes or using interferometric techniques that combine light from multiple telescopes, could reveal this hidden structure. But for now, we have to work with what we can see and acknowledge the limitations. There's also temporal bias. We're seeing the system at one moment in its evolution. The state we observe might be typical or it might be unusual, a brief phase that doesn't represent the long-term average behavior. The star formation rate we measure might be at a peak about to decline or at a minimum about to spike. Long-term monitoring, observing the system repeatedly over years or decades, could reveal whether it's changing. But on human timescales, even millions of years are imperceptible for galactic processes. We'd need to wait longer than human civilization has existed to see noticeable changes in the structure of the bridge. So we rely on statistics instead, observing many similar systems at different stages and building up a picture of the typical evolution. We use simulations to connect the dots, to interpolate between observed snapshots and extrapolate backward and forward in time. It's not perfect, but it's the best we can do given the constraints of observation. Despite these limitations, the data we have is remarkably rich. It's telling a coherent story. Star formation in a tidal bridge. High metallicity gas pulled from the galaxies. Young stellar populations ionizing their surroundings. Ongoing enrichment from supernovae. Complex kinematics reflecting the gravitational dynamics of the collision. All the pieces fit together into a picture that makes physical sense and matches theoretical expectations, while also surprising us with details we hadn't anticipated. That's the hallmark of good science. Confirmatory in the broad strokes, surprising in the details. matching our general understanding while challenging us to refine our models, answering questions while raising new ones. And this discovery is already spawning follow-up research. Other teams are proposing observations of similar systems to see if this vigorous star formation in tidal bridges is common or unusual. Theorists are running new simulations to try to reproduce the observed properties and understand the underlying physics. Observers are looking at archival data from other telescopes to see if there are hints of this phenomenon that were missed before. This is how science progresses. One discovery builds on previous work and inspires future research. Each generation of scientists stands on the shoulders of those who came before, seeing a little farther, understanding a little more deeply, asking better questions. The bridge between these two colliding galaxies is now part of the scientific literature, documented in peer-reviewed papers, incorporated into models and theories, used as a test case for understanding star formation. And it will continue to be studied for years to come as new techniques are developed and new questions are asked. Let's zoom out one final time to the ultimate question. What does all of this mean for understanding our place in the universe? We've covered the physics, the chemistry, the technology, the observations. But what's the deeper significance? It comes back to the idea of cosmic context. We are not special, not in the center of the universe, not made of unique material, not exempt from the laws of physics. We are ordinary matter in an ordinary solar system, orbiting an ordinary star in an ordinary galaxy in an ordinary part of the universe. But ordinary doesn't mean insignificant. It means we're part of the whole, connected to everything else, subject to the same processes that shape stars and galaxies across cosmic space and time. The atoms in our bodies came from stellar nucleosynthesis, just like the atoms in that bridge. The forces that hold us together are the same forces sculpting galactic structures. We are the universe experiencing itself. And we're the part of the universe that can understand what's happening, that can look at a tidal bridge 400 million light-years away and recognize it as a stellar nursery, that can measure the wavelengths of light and deduce chemical compositions, temperatures, densities, velocities, that can build mathematical models to explain observations and make predictions, that can ask questions about the nature of reality and actually find answers. This capacity for understanding is perhaps the most remarkable thing in the entire cosmos. Matter organized in such a way that it can contemplate matter. Atoms arranged into brains that can comprehend atoms. The universe has created, in us, a way to know itself. Every discovery, every observation, every insight into how nature works is the universe learning about itself. When we point James Webb at a distant galaxy merger and discover star formation happening where we didn't expect it, we're not external observers studying a separate reality. We're part of the reality studying itself, consciousness emerging from matter and examining the matter from which it emerged. This is profound. This is meaningful, not because it serves some cosmic purpose or fulfills some predetermined plan, but because it's intrinsically fascinating, because understanding is valuable in its own right, because asking questions and finding answers is what gives meaning to our existence. We're temporary. Our lives, our civilization, even our species will eventually end. The sun will burn out. The earth will become uninhabitable. The Milky Way will merge with Andromeda. On long enough timescales, everything we know will be transformed or destroyed. But while we're here, we can learn. We can explore. We can understand. We can look at a bridge of stars between colliding galaxies and recognize it as a place where the universe is creating new suns, new possibilities, new potential for complexity, and maybe even new forms of consciousness. And that's beautiful. That's what makes it all worthwhile. The brief flicker of awareness in a vast, ancient cosmos. The momentary organization of matter into forms that can appreciate beauty, discover truth, and wonder at the magnificence of existence. This bridge of stars, glowing across 400 million light-years of space, is a message. Not a message intended for us, because the universe doesn't have intentions, but a message nonetheless, a testament to the creativity of nature. A demonstration that even in chaos and violence, order and beauty emerge. A reminder that we're part of something vast and wonderful and worthy of our attention and awe. So when you think about this discovery, about star formation in a tidal bridge revealed by the James Webb Space Telescope, remember what it represents. It's not just a scientific result, not just data for specialists to discuss. It's a window into the workings of the cosmos. It's evidence that we can understand the universe through observation and reason. It's a connection between us and the farthest reaches of space and time. It's a bridge, not just between galaxies, but between ignorance and knowledge, between isolation and connection, between the mundane and the profound. A bridge built of starlight and understanding, spanning the gulf between our small planet and the infinite expanse beyond. And we're standing on that bridge, looking both ways, seeing where we came from and where we're going, understanding our past and imagining our future, aware of our cosmic heritage and our cosmic destiny. That's the true discovery. Not just the stars forming in the space between colliding galaxies, but the recognition that we're part of the same story, made of the same stuff, shaped by the same forces, sharing the same cosmic journey from the Big Bang to wherever the universe is heading. We are stardust. We are the universe. We are the bridge between past and future, between matter and meaning, between the infinite cosmos and the finite moment of now. And in this moment, we understand a little more than we did before. We see a little farther. We appreciate a little more deeply the magnificent complexity and beauty of the reality we inhabit. That's what science gives us. That's what exploration reveals. That's what this discovery, and every discovery, ultimately means. We are awake in the universe. We are aware. We are beginning to understand. And there's so much more to learn.